Hi everyone, welcome back to the channel. Today we're going to just take a little sidestep from the course and present a 20-ton lifting check on a RC beam. So we have a 950 deep beam that's 700mm wide. We're using 20-ton by 500mm long lifting pins. The beam itself is 10 meters, 688mm long. The distance out to the lifter then is 2.138 meters. Just marking up the details here on the drawing so you can see. Finally, some notes on the beam. So again, here you can see we have 20-ton pins, 500mm long, our length, our thickness, and our width. And the unit weight is 17.875 ton. Okay, the concrete strength at 28 days will be C50-60. The rebar then in the beam that we will be trying to engage for the lifters is our 12mm links that are surrounding the lifting pin, and these are installed at 300mm centres. The beam itself makes up the roof slab of a shaft. I'll just hide the shaft here that we can just see the beam, so it's taken a fair amount of load. We use Trimble Connect for viewing IFCs. All our drawings are done in Tekla. We'll just get rid of these slabs, hone in on the beams. Okay, so we have our beams here. We'll just cut through them, show you a little bit about the 3D model, and we'll push in. Yep, so you can see a good bit of steel in the bottom. Beams are working fairly hard, but in terms of the lifters, which is all we're worried about here, we have our links, which is a 4-legged B12 link at 300mm centres. And we have our two lifters, which are our 20-ton lifting pins at 500mm centres. Okay, so moving on to the Excel spreadsheet now. We have different spreadsheets for different precast ones for our beams that would have just two lifters. So we're looking here at beam demold and lift. We have a plan view of the beam. We have our two lifters, and we have all the different dimensions that will come from what we pop in. So it is a detailed spreadsheet, there's no doubt about it. But after the course and after the 6 weeks, you'll definitely have the tools to be able to build this. Whether you build it to this kind of detail or not, it'll be up to yourselves. It'll be all based on standard products and things like that. We do so many products, we need so many sheets, but they're all based on the same types of checks. Now, the thing with this spreadsheet here is that obviously we've been at it for a couple of years. Your first one, your Mark 1, version 1, let's call it, will it'll be a lot less powerful probably than what we can do here. But what we have is our orange cells where we input the data. So from the drawings there, the beam is 10,688, it's 700 wide, and it's 950 deep. The distance to the first lifter is 2138, and the edge distance in from the side is 350. Okay, now if we scoop down, first of all, just to show that we are lifting pins, we're taking a 20-ton lifting pin, 500 deep, okay, because that's important. The depth of the pin is important, what depth we can use, because for C1 and C2, which is the distance for our concrete cone, okay, so C1 and C2, the max we can use is 772.5, okay, so even though we're 2138, we can't take this concrete, we're only taking the concrete that's surrounding the lifter, and we can go 772.5. We have a little max CR here that's jumping out and it's telling us the 772 is the max we can take. So if we had a really wide beam, we could definitely go 772, but all directions. But because we're limited to 350 here, C3 and C4 with 350. Okay, the weight of the unit is 177 kilonewtons, which is fine. Our partial factor for lifting and handling, we're leaving that as 1 because we're using cracked concrete. Our partial factor for lifting and handling is 1.2. We can reduce that down from 1.35 as per the codes allow us to reduce that back to 1.2. Our partial factor for concrete is 1.5, for steel is 1.15, which is all standard. Okay, so in the factory we're saying that we have two lifters and we're lifting out of a tower crane, usually our gantry, so we can reduce back to 1.2. and our cable angles are 30 degrees. First site, again, same two lifters. We're 1.4 here because it's pretty mobile crane, and again to 30 degrees. Okay, so that's all we're doing there. In terms of adhesion to the mold, it's oil, that's 1, and the area will be the bottom of the beam, which is the 10,688 length by the 700 width. Okay, so that's all the 7.48 comes from. Moving down, then we get our the demands on the anchor. So the tension loads in the chains on site in the factory, the tension load on the anchors, and then the shear load of the anchors. Okay, so these are our demands. Again, earlier I said we were using a lifting pin, 20 tons, 500 long. The little E is the embedment of 15 mil that the pin is down from the top of the unit. So 515 will be the depth from the surface of the concrete down to the bottom of the pin. Our unit is 950, so we're fine. We have plenty of room underneath it for cover. So the first check is concrete cone. Okay, so step 3A, concrete cone failure. All our numbers are in here. Again, I said the orange is the only number we have to input manually, and that is literally, are we going to check it to CN TR 15728, or are we going to check it to ISEN 1992-4 for cracked concrete, or are we going to check it to that same code for uncracked concrete? And as I said to you, to be conservative, we're going to check it for cracked concrete. Okay, so moving down, here's where we pick the concrete strength, and we're saying that we have a 20, it'll be equivalent to a C2025, so 25 cube at factory and 50 cube on site. That's actually 50-60. So we 50-60 for site. Okay, again, our moving down to the maximum pull-out capacity of the concrete, and you'll see just 7.5 is all we pop in there. All these numbers are populating as we go. Step 3C is check the maximum blowout capacity for the anchors close to the edge. It's not required because there's a little in over here. You'll see where we have the part of the code tells it's okay if the embedment depth is the edge distance is not less than half the embedment depth. It's therefore blowout failure does not need to be checked. Okay, so the next check is check step 3D is splitting. For splitting, we have in the factory and on site, okay, and our reduced splitting capacity is 153 kilonewtons and then 243 for site. So we do get a lot more bang for our buck because of the concrete strength. Okay, step 4A, concrete edge failure. We have, is just, first of all, is this check required? Yes, we're going to say yes it is. Angle of shear force to the concrete edge. Okay, so what we have is our 350. We have our lifting pin and we're pulling this direction into the long direction. Okay, so that's why it's 90 degrees. We could change it up to 0. You'll see them here. So it's 0 if it's out towards the edge, which we're not. We're going at 90 degrees. So this is us here. All right. Again, all our numbers populate and go and slow down here so you can pause and check and have a look at the numbers, see if you're getting the same numbers. Okay, we have 4B and 4C, which is local concrete crushing and concrete pry-out. Now, this is where our sheet kind of tells us, are we okay or not okay? Green is okay, red is not okay. It's fairly straightforward. We can see that all checks pretty much pass bar concrete cone failure. So step 3A, if we go back up to 3A, our very first check. So it's saying that concrete cone failure, okay, 3A is not passing, right? So what does that mean? We have 109, so we're just 9% over. We could do a number of things here to get this to pass without having to rely on steel, but because we do want to have a check and pop in the steel that we have just for this example, but you could go back up and you could increase the concrete strength at lifting. You could decrease the angle of lift from 30 degrees back down, and that would all help and probably pass. Okay, so interaction check, we're at 160. And what we need to say now is that we're going to use some additional steel. Are we going to use some additional steel? Yes, because it's there, we might as well take advantage of it. Okay, so the part 6A is if we need some tension, additional tension steel, check what's in the unit. So you can see here's our lifter. We have some links either side. This is a section taken through it. So we do have this bar as per the 3D drawn that was shown earlier on the screen and the PDF. We have 12s at 300. So I've typed that in here. So from the provided information, we have B12 at 300. on both face direction to pull. Okay, what this tells us here is that we can use the steel within 0.75 times H effective, and we have our dimension for H effective in there is 386. So let's call it 400. So within an 800 distance, we can use whatever steel we have in there. Okay, so we have a 12 mil bar, we have 8 number of them, 300 centers are in there, and we get a total capacity of 393, which is greater than demand, so we're at 38%. Okay, then we need to check for splitting. So splitting will be what steel do we have out here on the side that's going to prevent it from splitting. Now we have bars, we have 12s at 300 centers from our drawing. We do have a lot of lacers, the lacer 16s, so the steel is an awful lot greater, but just for being conservative, I've just taken 12s at 300, which is 377 millimeters squared, and we need 172, so again, be 46%, so we're greater, everything is okay. The last check we want to do is assess the need for additional shear requirements for shear. Now, we don't have a load going out in that direction. Okay, so if we did have a load going out towards the edge, then our links that are there, we'd be able to use them, or we'd add in additional, usually a bit of containment either side might be necessary, but we don't have a load going out towards the edge. Our load is going north to south, so we don't have anything. We can have zero in there. If we work our way back up here to our summary page, so we said yes because we needed the steel, and you can see the new interaction check using the steel is 60%. So we're after getting from 160 down to 60 by using the steel that's in the beam. So a lot of the time, the steel that's already in the beam, once you know what checks to do and are able to calculate your demands and are able to calculate your capacities from the steel that's in the unit, you will find that the majority of the time the steel that's in there is okay and will resist the demands on the anchor. Not always, but it's definitely worth checking that first before you start having to add U-bars and additional steel around that unit, around that lifting pin. Okay, hope this is helpful, and I hope it kind of explains that why we're doing this 6-week course and why you're trying to get as much out as you can, because at the end of it, what you want is a spreadsheet that can design the lifting for a beam there in 15 or 20 minutes. Now, they're not always as easy and as straightforward as just a simple beam, but it's a start, and it'll hopefully get you going. Okay, thank you very much.